All right. A question of a bucket accelerating down a slope, and the question is, what is the angle that the surface makes with respect to the horizon, or the sloping bottom, and so on. So we're going to take it the angle with respect to the horizon. All right. So first of all, the question is about the angle that that water makes, and we know that on the water surface, dp has to be equal to 0. But what is dp? dpp is both a function of x and z, so therefore dp is dp dx dx plus dp dz dz, right? So if we set this equal to 0, we conclude that therefore dz dx, which is the equation of the line or slope of the line with respect to horizon, is equal to negative dx, yeah, so that becomes dp dx over dp dz. All right, and dz dx is really the tangent of the angle that that thing makes, the water surface makes. This is tangent alpha with the horizon. All right, good. Now we have to use, from this point on, you just close your eyes, you just follow the rules, right? What are the rules? Well, the governing equation for pressure in the case of a hydrostatic, and hydrostatic is a good assumption for this problem, is dp dx is equal to negative rho ax, and dp dz is equal to negative rho g plus az. All right, now a is along the sloping bottom, so therefore this angle is theta. So a has two components. The component in the x direction is a cosine theta, and there's a component in the z direction, I show it by green, and that's going to be a sine theta. Therefore ax is a cosine theta, and az is negative a sine theta. Okay, so all we need to do is just substitute this into the expression that we have here. So therefore this is negative rho, and instead of ax I just put a cosine theta, and in the expression below, minus rho times g plus well, minus, because a is negative a sine theta, and that's it. So therefore tangent alpha is equal to, as we said, negative dp dx over I'm sorry, there's just one negative sign here, minus dp dx over dp dz. So now let's substitute. That's going to be negative rho, oh, there's a minus sign here in front first, minus negative rho a cosine theta divided by negative rho g minus a sine theta, right? And then rho goes away, minus here goes away, so we're going to left with minus a cosine theta divided by g minus a sine theta. So this is tangent alpha. From here we can actually calculate what alpha is, and as you can see, alpha is negative, right? So it's basically below the horizon, so it's negative. And from this point on, calculating everything that is asked in the problem is just geometry, right? So if someone says, well, what is this height? It's not a good one. I'll just zoom in a little bit. If someone says, well, this is a center line, and then calculate for me this height, then of course it's easy, right? So first of all, you know what this height is, the h1 is, and in order to calculate h2, all you need to do is to, this is a right angle, you need to find this angle, right? And then what we know is, again, just draw the picture and do the calculation yourself, right? We know that Well, if I draw this line here, then this angle is the same as theta. So this angle is theta. We just got alpha, which is this little angle here. So the green angle, let's call it gamma. I'm sorry, the red one, the gamma, is equal to theta minus alpha, right? So theta is whatever is given in the problem. Alpha is what we just got, and then that gives us gamma, and therefore that H2, let's call this H2. Therefore H2 is simply the half of this length, whatever it is, this distance, let's call it, say, maybe B. So it's going to be B times tangent of gamma. So all I'm saying is that the rest of it is just geometry, and there's no fluid mechanics left to be worked out. But basically what you need to do is this. Just calculate A, just put in the equation, don't get confused, and use the Cartesian frame of coordinate with z-axis axis aligned with the gravitational acceleration, and you're going to be all set.